Welcome back. We're in lesson 30 in Algebra 2. If y'all hear a racket, sounds like something crying, it is my dog at the door. He is not allowed in right now because he has been passing some major gas. And it stinks, and I can't stand it. My nose has had all it can take. So, you might hear him cry. I'm not being mean. I'm just trying to help you teach or help you learn your Algebra 2 without passing out. So lesson 30. We are going to talk about deductive reasoning. And he is throwing me off so bad, y'all. He's so pitiful. Deductive reasoning is the term that we apply to a process of reasoning from a non-reversible statement that we call a major premise to a result called the conclusion. And this is, for those of you in my logic class, called a syllogism. Very good. For those of you that got that right, I'm so proud. So here's a couple of proofs or syllogisms that start with a major premise, they have a minor premise, and then they follow through to a conclusion. So here's a major premise for us that we might use. All squares are rectangles. We know that to be true. A square is a special type of rectangle. It's a regular rectangle. And our minor premise is that quadrilateral A, B, C, D is a square. So therefore, we can conclude that quadrilateral A, B, C, D is a rectangle. This would be a valid conclusion to this syllogism, that quadrilateral ABCD is a rectangle because it is a square and all squares are rectangles. We work ourselves from one major premise into a conclusion following a logical progression or a logical progression of statements. This is called a valid argument. It's also called a sound argument because every one of the premises in the conclusion are true. It's not just valid in the sense that it makes sense logically. It's valid, it's sound because it is in fact true in relation to reality. We could say something along the lines of all pens have blue ink. Then we could say Tracy has a pen. Tracy's pen has blue ink. It's valid because it follows a logical progression. But what if Tracy's pen has red ink? It's not sound because it's not provable in regards to this statement here. This is the major premise is not a valid statement. So therefore, the entire syllogism is not valid. Or I'm sorry, is not sound. It's valid because it follows logical progression, but it's not sound because the major premise is not true. All right, so that's kind of a little bit about syllogisms and the deductive reasoning that we use when we look at geometric shapes, and we're fixing to get into that. So let me clear the page. This is just a little bit of something fun to introduce you to that concept of deductive reasoning. A long time ago, the book tells, like, has paragraphs and paragraphs about Euclid. I'm not reading all of that for you. What I would like for you to do, though, in your spare time, when you're not doing all this wonderful Algebra 2 homework, go and Google Euclid and see who he was, and look at the contributions that he made to mathematics and geometry in particular. He was this guy who lived about 380 or 320 to 280 BC before Christ, and that's probably about 2,400 years ago. He marched through every aspect of geometry and wrote books about it. He wrote 13 volumes, in fact, and he looked at every aspect of lines and points and shapes and angles and how they related to one another, and what the logic that was behind them. And he made several, like 465, I think, postulates and theorems that we still use today, that are still valid today. And he called them axioms or postulates because he said they were self-evident truths. One of those self-evident truths that we have used repeatedly is that all right angles are equal. That's one of his postulates. We know this to be true. We're able to measure it and find out. But we know if something is perpendicular, it creates a right angle, and all four of the angles that created by those perpendicular lines will be congruent to one another. That's because of his postulate. We don't have to test that theory. We accept that self-evident truth because we can see it, right? Another postulate that he said was number 7. If equals be added to equals, the sums are equal. All right, that sounds confusing, but what he's saying is if you have 3 equals 3, these are equals. If equals be added to them, so let's say we add 2 to both sides, then we end up with 5 equals 5. So what he is saying is another way that we say whatever you do to one side, do to the other. We say that to include both addition and subtraction, multiplication and division. All of those things fall under the statement that we make, but they all tie back to his several postulates that he made. He also made one about subtraction. If equals be subtracted from equals, then they will remain equals. So that's all. Ooh, I'm sorry. That's all he's saying is keep the equation true by doing whatever you do on one side, you do to the other side, and it remains balanced. It remains equal. So we're using all of his postulates without even realizing what we're doing or that we're using them. We're walking through his logical statements in Algebra 1 and Algebra 2. And postulate number 10, the whole is greater than any part. So he's saying that one whole set of something is greater than any fraction. Even though 2 is greater than 1 and 3 is greater than 1, this is not a whole. This is a part. It's a fractional part of the whole. And the whole is always going to be more than a fractional part. Regardless of what number the numerator and the denominator are, regardless of how many pieces you divide this into, the whole set is still more than any little piece. So basic truths like that we accept now, we accept them now because of Euclid and his march through geometry and mathematics. He has helped set the stage for us today. And in my opinion, he has helped to define and show us the way that God ordered the world when he created it. And understanding math, to me, is trying to understand how amazingly intricate and ordered that our world is, which just proves to me that it had to be done by somebody. None of this is an accident. When everything lines up the way that it lines up, it's proof to me that there is a creator and we weren't just an accidental Big Bang. Just it's too precise. And I'll show you more about that as we move forward. Okay, all right, guys. I'm sorry. I had to pause and let the dog in because he's driving me nuts. So he might bother me and bug us a little bit more. So let's talk about vertical angles that are equal, and let's show how these things line up with what we're talking about. So if we have a pair of lines and they cross at some angle, we can actually prove that these lines, these angles here are corresponding. So let's say we have X and Y here. Okay, and then we have A and B here. We can actually prove that A and B are equal to one another without even having to define their measure. And here's how we can do that. So we know that A and X lie against a straight line, and we know that an angle, a straight line or straight angle, is 180 degrees because it's exactly half of a circle. It's the diameter. You have a circle here and you cut a diameter. We know circle is 360 degrees and half of that is 180. We know that, right? So we know that that straight angle is 180 degrees. Right? So if we have A plus X on this line equal to 180, right? And then along this line, another straight angle, we have X plus B is also 180. These two things are congruent, and because of Euclid's logic, we are told, or he told us, that things that are equal to the same thing are equal to each other. That was Postulate 6. And it's because these things are equal to the same thing, they're equal to each other. So we could say that A plus X equals X plus B. And so just using logic and what we know, what Euclid told us, is that if we subtract the same things from the same things, if we subtract equals from equals, so we subtract X, the same thing from the same thing, these will contradict each other, cancel out, then we're left with A equals B. That proves that opposite angles are congruent, right? So that, without even doing the math, right? Without even doing any real math, we prove that those two angles are congruent. And those are some things that are part of what Euclid proved through his march through geometry. He showed those types of illustrations. Here's another illustration that he talked about, and that was with a corresponding interior and exterior angles. So if we have here a couple of parallel lines and we have a transversal that is perpendicular, right? It's perpendicular to this parallel line, creates a right angle. We know this is a right angle, and because it's 90, this is a right angle. And then this one is a right angle because they are opposite. We've already proven that opposite angles are true. So these two are 90, so these two have to be 90 because 90 and 90 equal 180. We also know, because they are perpendicular and this is a parallel line is equal to this line, that all of these angles are going to be right angles, and these are all going to be congruent to all of these. Okay, and this was, I think, lesson 1. It's when we postulated that when parallel lines are cut by a transversal that's perpendicular, all the angles formed are right angles, and we see this in this figure. Now, if the angles are not right angles, so we have a set of parallel lines here, and we draw a transversal. Okay, we've postulated that half the angles are small angles and the other half are large angles, and when those angles are added together, this is the large one and this is the small one, when these angles are added together, they'll be 180, right? So because we know that this is going to be congruent to this angle, right? This is a large angle as well. And because of the rule of parallel lines, we already know that this is going to be parallel to this or congruent to this. And because it's opposite this one, this is going to be the same measure. So we can tell without doing the math which angles are going to be congruent to one another. We don't have to get the degree of measure to know which ones are which. We also know, because of Euclid, that alternate interior angles are going to be congruent as well. So this angle is opposite this. This angle is opposite this. We know that this angle and this angle make 180. This angle and this angle make 180. And this is the opposite angle to that, so this angle and this angle have to equal one another as well. If that makes any sense. I might have gone a little too fast. So these are called, these interior angles that are on opposite sides, these are called alternate angles, and they have a congruent measure. So alternate angles equal each other, or alternate angles equal. So this is an alternate, and by alternate it just means it flips to the side and stays on top. Congruent angles are on the same side in the same position. This large angle and this large angle, these are alternate angles, and they're alternate interior angles because they are in between the two parallel lines. These angles on the outside here and these angles on the outside of the parallel lines, those are exterior angles because they're exterior to the figure. It's like being indoors or outdoors. You're either inside the walls or you're outside the walls. So this is interior angles and these are exterior angles. Pretty straightforward. That one's pretty easy to understand. All right, so I have one more thing to talk about, and that is that triangles, we're going to do a proof that proves that triangles are equal to 180 degrees. And I'm going to show you that visually. So let's say we have a line here, right? And we have a line here. They're parallel lines. And we're going to do a transversal here. And we're going to do a transversal here. Just like that, right? And we're going to label these angles. This is going to be B. This is going to be A. And this is going to be C, right? Now, because of what we learned about transversals and alternate interior angles, we know that this angle is going to be congruent to this angle right here, just like that. So that means that this angle and this angle are alternate interior angles. So this is the same as angle A, right? All right, by the same logic, you know, this angle and this angle are congruent. So that means this angle and this angle will be congruent. So we have the same measure as angle C here. All right, where was I? I had to pause, sorry. So because angle C and this angle are alternate interior angles, the measure of this angle is equal to the measure of this angle. Now, because we know that a straight angle is equal to 180 degrees, we know that A plus B plus C equals 180, right? So A, which is congruent here, A plus B plus C, which is congruent here, also equals 180. And it doesn't matter at what degree this angle is. This transversal could be acute or obtuse or whatever it is. Those three angles are still going to correspond to the angles that are on the inside here and here, and they're going to equal 180 degrees because they are alternate interior angles that are congruent to one another. And that, my dear ladies or students, is how we prove that a triangle contains 180 degrees. All right, there's another way that you could do it. Is not necessarily as sound, but it makes sense to me. And that is, it's the way we find area of a triangle. You have a square. We know that a square contains 4 90-degree angles, right? 4 times 90 is 360. Any rectangle has 4 90-degree angles. That equals a total interior degree of measure of 360. When we form a triangle, we cut that rectangle effectively in half, regardless of what size or shape it is. We also cut the degree of measure in half. 360 divided by 2 is 180. So you get 90, 45, and 45, which equals 180. And then regardless of where you move those points, whatever shape that rectangle might be, you're still going to get 180. And that, to me, knowing that there's two ways that you can illustrate the same number, the same degree of measure, looking at it from two different perspectives, it just shows to me that none of this was an accident, that all of this math and science and this world was designed by somebody who knew way more than we did. This intricate, this minute detail, it's not an accident. It's on purpose. And that, to me, the more I learn about math and the more I understand math and geometry proofs and the way we have learned to understand how the world fits together, the more it just proves the existence of a creator and our God. And I hope that you start to see the beauty of mathematics in that way, in how it points to God and points to all of this being ordered and orderly on purpose by Him. And that is all I have for lesson 30. So I will see you guys in lesson 31.